Hey, this is how schools teach you calculus. This is how I'm going to teach you calculus. As long as you know a little bit of algebra, I'm going to be able to guide you through truly understanding what it means to differentiate something and integrate something, why you would even care about these things, what do they mean, how would you use them in a problem, things like that. So, to start off, here's this nice, simple line on this graph, and we're going to start off with differentiation. And all you really need to know what that means, if you take one thing away from this, it's this. All it means is it's change. A change in something over usually time or space. So if you remember slope or m or y2 minus y1 over x2 minus x1 or rise over run, all basically mean the same thing. It's just slope or change in something. So, for example, for this line, it's very easy. You don't need calculus to know what the derivative of this is. So you just take the change in y. So I'm going to start here at 0.2. I'm going to go up 2 in y. I'm going to go 4 over in x. So I'm still on the line there. So that's the change in 2 over 4, or 1/2. You could also just read the 1/2 here, and you can see that indeed that is correct. That is the slope. So for lines, you don't even need anything fancy. You can just look at 2 points, find the slope from that. Where we need calculus is where the line gets wavy and it changes over time and the slope changes over time, and it's not easy to just pick 2 points and find the slope here. So here I picked, or I put out 2 points on the plot here that follow the line, and you can see that black line is the slope that goes through those 2 points. So if we want to find the slope on a particular point on this line, it helps if the points that we pick that determine the slope are closer together. So if you notice, the closer I bring these points together, the more accurate the slope line connects with the graph. So that's the key takeaway here. We're doing the same thing as what we did with the line, where we have 2 points and then we find the slope between them. But for a curved line, we're going to try making them as close together as possible. And here you can see, for example, there's the slope formula. Doing nothing fancy here. So the first takeaway is this. Instead of just picking 2 arbitrary points to draw a slope line through, what we can do is take 1 point and then have the second point be related to the first point, but just have some constant distance d away. So here I have x1 just set to whatever, but here x2 is x1, but just plus some distance away. So here I have it set to 3. And just notice when I move x1, that second point is automatically just going to move at a set distance away. So the key here is setting the two to be related like that, and then to simply lower the d value. And as I lower the d value, the distance between those 2 points are going to get closer and closer. They're going to get really close, and at some point they'll be so close. You can see now I'm moving those 2 points in unison across the line, and that slope line is pretty accurately following along the curve. And that's basically the trick we're going to do for differentiation. That's basically what it is. It's just bringing those 2 points really close together. Again, differentiation is just slope. It's just change over time or space. So if you remember from algebra, y2 over y1 over x2 minus x1, this is what I'm going to use to demonstrate the definition of a derivative, basically. So first of all, I'm going to change the meaning of y to f of x. So y is just your output you get when you put an x. So if we go back to the graph here, your x is along this axis, and then your y is going to go up and down here. So f of x and y, it's the same thing. It's you plug in some x to get some y value. So it's just an input and output sort of deal. So I'm going to rename it to be like that. So what we have here is m equals f of x2 minus f of x1 over x2 minus x1. And we're going to do that same trick that I showed you where we relate x2 to x1, where x2 is going to be just x1, but with some distance. And for the sake of convention, I'm going to call it delta x. This was our d variable when I showed you the graph, but this is just standard notation. So you can call this delta x. So I'm going to make x2 equal to that. And we're going to see what happens to this m equation. So these two variables, plus or minus, they cancel out. Maybe I should use a different color for that. I'll use red, I suppose. So it's going to be that. This is basically it. We can get rid of. I'm not angry anymore. Sorry. Hold on. We can get rid of the x1s here's at the x1 here at this point. The specific point doesn't really matter. So what we did here is basically we went from finding the slope of a specific point into finding the slope of all points, where instead of picking a specific point x1, we're just going to say x. You can put whatever you want in here and you're going to get the slope across the entire line. And I guess you want to be technical about it. As long as the line is continuous, if you're differentiating a line that's continuous between some bounds, you can find the slope of that line between those same bounds. There is one little notation I will have to introduce, because we said this delta x here should get small. So we're going to basically codify that mathematically. So this is called limit. And all I'm saying is that delta x here is going to approach 0. That distance that I talked about is going to approach 0. So if you don't mind me just moving it down here like that, this is what we're talking about. So that's the only other condition. We're going to make this get as close to 0 as possible. And then these terms that cancel out, this is what the form looks like. So as for like an explicit example of how you'd use this, I'll make a function here, f of x equals 2x squared minus 4x plus 1. So to use this, first we need f of x, which we have here already defined, but we need f of x plus delta x. So how we're going to do that is basically substitution. So really, when you change the form to something like this, you just replace all the x's with whatever you put in here. So in this case, it's going to be so now that we have these, we're going to substitute those values into here. And I'm going to try and just copy paste because that's a lot to rewrite. But limit delta x goes to 0. So we have f of x plus delta x, which is all of that. Just bring that up here. And then minus the f of x, which is over here. Because it's minus, we got to flip all the signs. So just don't forget that. And all of that's going to be over delta x. Over delta x. So one thing to note is there's a lot of cancellation that happens. This 2x squared and this minus 2x squared, this plus 4x, this minus 4x, this minus 1. And I just realized, I believe I messed up because I copied minus 1 here when it should be a plus 1, which means that should be a plus 1 and that should be a plus 1. That's my bad. All right, so the minus 1 and then the plus 1 here. So notice that when you take the difference between f of x plus delta x and then the f of x, these x terms all vanish. You're just left with these delta x terms. All we get are these delta x terms, which means we can actually perform this division with the delta x on the bottom. Because if you haven't noticed, if we were to just take this limit right now and replace all the delta x's with zeros, you would get division by 0 here, and you don't want that. So this is all actually We can just remove delta x from each of these. Remove, remove, remove. Now we can do this substitution where we're taking delta x all the way to 0. So that means this goes to 0, and you are left with 4x minus 4. And this is indeed the derivative of this. All right, so what does this mean though? We found the change, we found all of the changes across all of the x's here. You put in any x you want to find the slope of in this equation. So let's say x equals 1. And to find the slope, you just take this equation and plug that same 1 into this form, which is 4x minus 4. So in that case, it'd be 0. And I'll show a graph to prove that that is in fact going to be 0 at x equals 1. But typically, so f of x was this. When you take the derivative of something, of f of x, you would call it f prime of x. You would just put this little apostrophe thing here. So this is the slope equation for this, for all points for where you plug in x. So now, let me go back to here, because I do have a little demonstration here. So this is that form, 2x squared minus 4 plus 1. Here is our derivative line that we just calculated, 4x minus 4. So you can see when this line hits the 0, the slope of our original equation, which is in red, is 0. And you'll notice to the left of x equals 1, it goes to negative. And similarly, the slope of the red line left of 1 is also negative. This is no coincidence. Oh, I turned the line green somehow. But so if you go to the right of the blue line of x equals 1, it's positive, and then the parabola here, the slope gets positive. So that is the correlation. And you can see here I set x0 equals 1, and indeed at x0 equals 1, the slope line is flat. There is no slope there, which is 0, which is what I said it would be. So that is basically differentiation. And this is a little bonus for some of you that are wondering, well, we found this is basically what that m value was, right? M is slope, and you might remember a certain equation, y equals mx plus b, where m was the slope and b is this y-intercept. Well, does this b come into play? And yes. So if you ever had to do a problem with finding the equation of the slope line that passes a certain point, you need this slope intercept. So I'm going to show you really quick just how to do that. But first of all, I'm going to reformat this to use f of x. And then instead of m, remember derivative, you call it f prime of x. And then there's one other thing I gotta point out is we want a slope line at a specific point. We're not gonna put in this as is, because this is finding the slope for all points. We just want a specific point. So I'm gonna put in some specific x value, x of 0, into this slope. So for some x0, this is the slope at that point. So this is the equation we want to solve. We're going to solve for b. So how we're going to do that is, firstly, we're going to find the y-intercept at x0. So now I'm going to put in x of 0 into f here. So I'm going to replace all x's on this side with also x0s. And then I'm going to rearrange terms so I get b on one side. And then this is what that looks like. So that's it. That's what b is supposed to be. So now if I substitute b back into this equation where I wanted to find b, and there we go. This is that equation. This is the slope line equation at a certain point. And if we go back to how I drew this black line in the first place, you'll see this equation here is me just using this form that I just found right here. So that is the exact same thing as this, only I actually plugged in the 2x squared minus 4x plus 1, and then the derivative here. I plugged in my x zeros, so you are getting the slope line at a certain point now. And if I go ahead and move this x point, you can see the slope line perfectly touches the green line at the specific point. So really, that's all you need to know about differentiation. All of those rules that you might have gotten as like a printout to like memorize, those all derive from doing this limit definition process or things similar to this, where you would just go through all this. And really, those rules are just patterns that you find for like polynomials and other things. If differentiation is basically just change, then what is integration? Well, let me clear this out first. Integration is, you can think of it as just sums, summing, addition, whatever. So I'm going to give a concrete example here. Both of differentiation and integration. It's going to be a simpler case. It's not going to be exactly that, but this will demonstrate what I'm trying to talk about here. So imagine these numbers. Maybe you're like walking somewhere and you're keeping track of how many meters you walked. So you started at 12 and then you measure a bit later and you went and you're at 16 meters and then 23 and so on. So firstly, the idea of this is differentiating and integration are inverse functions of each other. So changes versus sums, if you apply both of these, they'll basically cancel each other out and you'll get back your original function. So that's the idea. If you take all these changes and then you take the sum of those changes, you'll get back what you started. So for example, I'll take the change of all these numbers over time. So to get from 12 to 16, it's plus 4. And then we have plus 7 to go from 16 to 23. And then plus 8. And then plus 3. So you can think of this kind of as differentiation. I'm taking just the changes of all the numbers over time. So now let me go do the sums. So now I'm going to take the sums of all these changes of numbers. So I'm going to start at 4. So that makes 4. Plus 7 is 11. Plus 8 is 19. And then plus 3 is 22. Now notice we took the sums of the differences, and 22 is not, in fact, 34. We, in fact, lost some information, and this will be important to keep in mind for much later. But in this case, we need the initial distance that we traveled, which is 12. So if you do 22 plus 12 here, you'll see we'll get back 34. And to kind of illustrate like what this differentiating and then integration thing, let me try doing it the other way. These are the sums. So plus 16 is 28, plus 23 is 51, plus 31 is 82, etc. And now I'm going to take the change of these sums. So now instead of going differences, sums, I'm going to go sums, then differences, and we're going to see what happens. So that's plus 16 plus 23, 51 to 82 is 31, and then 34. So look at that. We have 16, 16, 23, 23, 31, 31, 34, 34. In this case, when we did the operations in this way, we got back our original numbers that we're looking for. So again, just something to keep in mind, but hopefully this illustrates what I'm talking about when I'm talking about differentiating versus integration. Integration is sums. So let's do a sum right now. This describes this line that goes through these 2 points. What do I mean by the sum in this case? All I mean is you're taking the area under this line. This is basically a triangle. You stop at the x-axis here. So we just want the sum of this triangle. And we know what the sums of triangles are. We do not need calculus. We do not need integration for that. It's just half of base times height. The base here looks like it's 4. So 1/2, 4. And then the height is 2. And that will give us 4. So the area under this triangle is 4. Just like with the simple line for finding the slope, we don't need calculus. We can just figure it out using elementary geometry, math, whatever. So of course the problem is going to be when we take a curved line sum, because we don't know intuitively, what the area under this curve would be. What I'm going to do now is we're going to try an alternate way of summing this. We're going to use just rectangles, a bunch of rectangles. So here I'm going to divide this up into 4 pieces. So this is x equals 1, x equals 2, x equals 3, x equals 4. And then for each one of these integers, I'm going to make a rectangle that goes up until it hits this line and then goes across 1 unit. So for x equals 2, I'm going to do the same thing. Goes across 1 unit, stops at the line every time. And this is going to be our first guess. I'm going to say we're going to estimate the area like this. And the advantage of this is if the line was sloped, we can just make rectangles that reach up until it hits the slope, and then basically get a different set of rectangles that kind of follow the line. So that's the idea here. If you don't know sigma notation, a quick refresher, this means we're going to start at 0, and we're going to have this variable here. I don't know if maybe you've done programming. This would make a little more sense. We set I to 0, and we're going to iterate it up until we hit 4. In this case, all we're doing is summing rectangles. The area of a rectangle is just width times height. Well, I set all these to 1 wide each, so it's really just going to be a width of 1 for all of them. So width is 1 for all of them, and then the height, I made the height dependent on where this x value was. And actually, I just realized we should start at 1, because then it's I equals 1, then 2, then 3, then 4. The height is just going to be whatever our function is, because the function is the height here of I. Because if you plug in I equals 1 here, that's f of 1. So that's the y value of x equals 1, which is here, which is what we want, the height. And then when we go up to I equals 2, we get the height of this rectangle, and so on. How this is going to play out, it's going to equal so this expands out to this. So here's our I equals 1 term, and we're adding it with the I equals 2 term, then the I equals 3 term, and the I equals 4 term. So this sums up, remember, we do know our f of x is 1/2 x. Plugging 1 into here, then 2, etc. will give us 1/2 plus 1 plus 3/2 plus 2. And our sum is 5. So it's a little off. Our actual value is 4, but we ended up with 5. You can see why that would make sense. All of our rectangles are accounting for extra area we didn't want. So we're going to overestimate with this method. But the solution to that really is to just use more rectangles. If we use more rectangles, then we'll have fewer, we have less area we're cutting over. This time, we're going to double the amount. And you can see there's less area here being overestimated. But we're going to see what happens to the summation now when we do this. So we're going to do another summation. And because we have 8 rectangles, we're going to go from 1 to 8. And then we're going to have our width times height. The width and the height are going to be different this time. We halved all of our rectangles' widths. So instead of 1 unit across, they're going to be 1/2 unit across. The height is going to be f of I over 2. Does this make sense? So we start at 1. We want the position, the y position at x equals 1/2, which would be here, this point. And then when I equals 2, we go to f of 1, which is when y equals 1 here. and so on up to 8. So I'm going to spare the details. When you go through these 8 sums, you end up with this value, 4.5. It's getting closer indeed to our true value of 4. So you might guess where this is going. We're just going to keep adding more rectangles. Basically, we're going to add an infinite number of rectangles. So how are we going to do this? Well, first of all, we got to do 2 things. This only really works for this range from 0 to 4. We're going to try and make it more generic. Imagine, again, this triangle, but now we don't want to say just find the area between these specific points. We're going to say you can pick any 2 points, and you want to find the area between any of these 2 points, and you can choose how many rectangles you want. You can choose all the rectangles you want, but just imagine the rectangles now stop here with these ranges. And we just want to find the area between them. How we would do that, let's keep the rectangles at 4 for now. We'll change the rectangle count later. So now we have, again, our width times height, but now our width is dependent on the range here. So really we want the length of this range. That's going to help us tell how wide the rectangle should be. And the length of that is just b minus a. So with this range, you want to divide it into 4 rectangles. So each width is going to be that over 4. This is the width of each rectangle now. So what is the height going to be? This is a little more tricky to understand. Note that for every time we go up by I, we're going to move over to the next rectangle, which takes 1 width worth of rectangle, if that makes sense. So we know there's going to be a change of a width of 1 rectangle every time, which is what this quantity is. That's what we figured out. So we know there's at least going to be a change of this for every I going up. So that's how you would write this. We're going up 1 rectangle width every time. And now we just need the starting position, which is A. So we start at A, and we go up this amount every time. So convince yourself that if I equals 1, we actually end up here, because we start at A, and then we go over 1 width of a rectangle. So that's what this looks like with basically non-explicit ranges. We can just define them into variables like this. And the second improvement we're going to make to this is use infinite rectangles. I'm just going to copy this because it's going to look very similar to what we had before. We're going to bring that limit notation back again. So I'm going to take a limit for some n. N is going to be our rectangle count. And we're going to say go to infinity. So what is that going to mean here? Well, instead of 4 to sum up here, we're going to go to n. And again, this n value is going to go to infinity. So now we have to change all the 4s. And this is our formula for finding the area under a curve using infinite rectangles for some range. And I'm going to prove to you that this is all you need to get this sum to work. Let's sum from 0 to 4 for this line. So f of x is going to be 1/2 x, and our range, our lower bound range is going to be a equals 0, and our upper bound is going to be b equals 4. So from 0 to 4, and let's see what happens. 4 minus 0 here is just 4. So that's just going to be 4 over n. For the same reason, this will be 4 over n. This plus a goes away because a is 0. So now you just end up with this form. And remember, with f, this was f of x, but now we're going to substitute all the x's we see up here with 4n times I. So that's what that looks like. Some things to note. We really, if we have like just all multiply terms like this, we can move terms to the left side of this if they don't depend on I. So notice that this, and this will be constant the entire time we're going up by I. So what we can really do here is move all this over to the left side. This is what we get. Let me make sure that's correct. Yeah, that looks correct. So this is the term we end up with. This, yeah, I think you would learn this in algebra. The summation formulas are what get used here. And this is the same thing as this. I'm not going to prove that here. It's just something you typically look up. When you take the sum of all of those i's from 1 to n, it becomes this. So we have, this is the same thing as n squared plus n. These can be multiplied together, so this makes 2, is it 2n squared? Yeah, 2n squared. And then we can combine this, so this is from 8 over 2 is now 4 over 1. And now I'm going to split the fraction up into two pieces. So this is 4n squared over n squared plus n over n squared. These n squared cancel out, and this n cancels with that one. So now we have this. Look at that. And guess what happens here? When we set n to infinity, this term will go to 1 over infinity. And 1 over a very, very, very large number tends to 0. So as n tends to infinity, this term tends to 0. And it cancels out, and you get 4. And this is the sum we were looking for. We're not done yet, because we found the area under a specific range. If you remember, when we took the derivative of a function, we were able to find the slope over an entire range at any point of the function we started with. So just like how we were able to find the slope of any point of a function, can we find the area if we pick any point of this function? Can we get another function relating to that? And the answer is yes, you can. And I'm going to show you how to do it. We're going to have to do a change in variables here. It's not going to change anything really, but I want to use x for something else already. So this curve line, I'm going to call it f of t. So the function of t, that means this is the t-axis now. And now this line is going to be f of t. I don't want a specific range from a to b. And how we're going to do that is I'm going to let b equal to x. For some x that we're going to put into here, so let's say x equals 3, we're going to get the area of the curve up to x equals 3. But we need a starting point too. And the way we're going to do it is we're going to set a to 0. We're going to start the sum from 0 every time, and we're going to go up to some x. So at any point x, we go down this line, we're going to find the area up to that point from 0. So how is that going to look with this? A equals 0 and b equals x means the a's all go away. So this is just x over n. This is x over n, and this is 0. Let's find the full antiderivative of this function. So now we can get the area for any point for all points. This is f of t equals 1 half x. Remember, we had a change of variables. And so what we're going to do is do what we did again. So 1 half of x. This function tells me to replace all the x's with this. So that's what I'm going to do. So now we have this form. And with this form, we can move this, this, and this to the left side because there's no I variables. It does not depend on I. So now, combining like terms, this becomes x squared over 2n n squared. And then I is all alone here. And just like last time, we know what this equals. It's going to equal, yes, I'm being lazy here, n times n plus 1 over 2. So just like last time, we're going to cancel out the n squared there, and n there. And just like last time, this value is going to get smaller and smaller as n gets larger and larger, and as n approaches infinity, this approaches 0. And this is what we get. X squared over 4. What we found is that for this function, you can plug in any t value you want here. So t equals 1, for example. And what this formula gives you when you plug in x equals 1 is the area from 0 to 1 for this. So we went from 0 to 4 for that one function. So if we put in 0 to 4, that's just setting x to 4 here, which is 4 squared over 4. Oh my god, that is the worst 4 I've ever drawn in my life, which is 16 over 4, which is 4. That is indeed what we started with. And now you know what it means to integrate something. This is it. You now know both differentiation and integration and what it means. And we're almost done. There's one other topic I need to bring up. So remember back when I had these numbers and we tried doing finding the changes of them and then the sums of them, and then we lost some information. So that's going to be important to understand. So let me give an example with like an actual function. So let's say we have some f of x equals 2x plus 1. Let's say that I want to find the integration. I want to integrate f of x. Now, when you integrate f of x, typically the format you would do that in is you would make this a capital F. So this is the antiderivative of that. And you get x squared plus x. I just know what that will turn into. So this is what happens when you take the sum of things first. And now I'm going to take the changes of that, or the derivative of that, and see what I end up with. And what I end up with is the exact same form that I started with. So just like when we started with the sums here, we went to sums and then to differences, we kept the same equation. Now in contrast, let's see what happens if I take the derivative of this function first. So I'm going to take the derivative, and I'm going to end up with 2. And when I take the antiderivative of this derivative, the sum of the changes, I end up with 2x. I lost that one information. I lost the constant. When we integrate, we need to add a constant of integration back, because if we want this change and sums to be true inverses of each other, we need some equalities to be upheld. And this equation here, we need to find all equations that satisfy this form. So that's when you take the derivative of it, you'll get back the correct value. And that constant of integration gives us a whole family of these where this is correct. Well, we'll get back our original function. And we can figure out what C is if we know some initial conditions. So let me give an example of that. Let's say that we know that when you take the antiderivative of something, that function, when you put in 0, is going to give us 3. But yeah, so let's say we have f of x equals 2x plus 1. So we'll take the antiderivative of that. So we'll get x squared plus x plus c. And this works. You take the derivative of this, and you'll get back this form. You get a whole family of solutions. But now, what we have here is an initial condition, which says that this, when you plug in 0 to this form, you'll get back 3. So we can find what c is now, which is, this is going to be, all the x's are zeros now, which means these are zeros. This is 3, which means c equals 3. So if you have an initial condition, you can fill out what c is here. And that's the full form. All right, this was quite a lot, but I think this was all of the essentials, and hopefully after going through this, you at least understand on a fundamental level what it means to differentiate something, what it means to integrate something, and why this plus C matters, and how you can basically derive everything that we know of how to do these like quick forms of integration and differentiation. Now you know calculus. Congratulations.